So today we're talking about Newton's third law. And the third law is the one that is most often remembered, but also I think the most often misunderstood. So for Newton's third law, first let's get to it here. It's not inertia. That would be the first law. Every object in motion stays in motion. Every object at rest stays at rest, meaning things keep on doing what it is that they are doing. It's not law of the second law, where force equals mass times acceleration, where we talk about how the force and the acceleration are directly proportional and the mass and the acceleration are inversely proportional. That's not what we're talking about. Instead, it's this one. For every action force, there is an equal and opposite reaction force. So let that sink in for a second. Action, reaction. People misconstrue this one. They say, well, he hit me, so I hit him. No. Don't blame Newton's third law on that one. That's just you being a punk. No. The third law states for every action force, there is an equal and opposite reaction force. So if you go and push on a wall, does the wall push back? Well, let me ask another question. Do you fall through the wall? Probably not. So there's evidence that the wall is pushing back on you. If you go kick a ball, do you feel that kick with your foot? Probably. Evidence of the reaction force. But let's go a little deeper here. Not just was the push and the pull, but let's talk about the horse and the cart. If the horse pulls the cart with a force of 1,000 newtons and the cart pulls on the horse with a force of 1,000 newtons, how, of course, does the horse move the cart if the force on the horse is equal to the force of the cart on the horse? That was a lot. But think about this for a second. Is the horse pulling on the cart? Yes. Does the horse feel a tug on its harness? Yeah, it's going to. So there's evidence of the backwards force. So if the horse is pulling forward with 1,000 and the cart's pulling back with 1,000, the question is, how does it move? Right here, because these red arrows, that's not how it moves. But you also have to think, well, that's not the only forces in action here. There's also forces located at the hooves. I want to move all this. Hold on now. The hoof pushes against the ground, and the ground pushes against the hoof. All four of them. Each hoof-ground interaction is going to be equal and opposite. Each hoof equal and opposite with the ground. Are there going to be resistance forces located at the wheels? Yeah, the wheel is going to push on the ground's going to push back up on the wheel. Resistance, it's going to resist motion. But the real key here is that the resistance forces located here at the wheel, they do not have to be anything like the forces at the hoof. And that is the whole point of this. The whole point of this is the idea of outside forces cause motion. One of my favorite, I guess, scenes out of the Lorax is at the end when he's all mad at everything and the Lorax grabs a hold of the scruff of his own neck and heists himself and lifts himself away. Can you reach around to your own back, grab your own backpack, and pick yourself up off the ground? No, that doesn't work. Because the you grabbing your backpack is an internal force. Internal forces don't cause motion. Okay, another example. You are standing on a skateboard. Your feet are both on the skateboard. If you grab your own wrist and pull on your own wrist, are you really going to go anywhere? No, not unless you fall off the skateboard or something. You're not going to go anywhere. But if you want to move yourself on the skateboard, do you put a foot to the ground and push off the ground, which then you now have an outside force of the ground pushing on the foot. And that is how you and the skateboard are able to move. Okay, next one. So let's ask this. How do you walk? Have you ever really, really paid attention to how the foot and the ground work together for walking? Do you ever think about it for a second here? I'll often ask the class in person. I'll say, okay, guys, tell me how to walk. And they'll say, okay, put one foot in front of the other. And I will indeed put one foot in front of the other. And then I'm like, okay, now what? Like, we'll pick up the other foot. Well, if I simply pick up the back foot, now I'm off balance. I'm just going to fall backwards. So it's more than just picking up the back foot. Then the kids will say, well, you got to shift your weight forward. And so I, in a very herky-jerky kind of way, I kind of lean myself forward and move a foot. And the kids like, yeah, like that. I'm like, is this really how you walk? Do you throw your weight forward as you walk? And like, well, no, that's not true. So it's much simpler than that. To walk forward, all you do is push backwards on the ground with your foot. And then you push backwards on the ground with that foot. Alternately, that's how you move. And how does that work? Because you're pushing backwards on the ground is pushing forwards on your foot. Okay, canoeing. If you want your canoe to go forward, do you take the paddle and push this way? No, that would make you go backwards. Instead, you take your paddle, you bring it forward, and you pull the water to the back. So you're applying a backward force on the water. The water is applying a forward force on your paddle, but that's not how you move. It's the fact that the forces located at the paddle are not the same as the forces located holding your boat still. That's how you move. Another example. You grab a hammer and a nail and you whack the hammer onto the nail. Is the force of the hammer on the nail the same as the force of the nail on the hammer? Yes, absolutely. Well, if those are the same, you're thinking, well, how does the nail go into the wood? Okay, move it down the pipe a little bit here. So you hit the hammer, you hit the nail with the hammer. Forces are translated through that nail at the wood, right? If the force of the hammer is equal to the force of the nail on the hammer, and then the force of the nail on the wood is equal to the force of the wood on the nail, which is true, how does the nail go into the wood? Same idea. It's outside forces. It's not that the nail on the wood and the wood on the nail are the same. It's that the force of the nail on the wood is greater than the forces holding the wood together. Is it easy to pound a nail into concrete? No, it's really not. Because the forces holding the concrete together are greater than the forces keeping the nail straight. All right. Oh, I guess there's a class change going on. Oh well. Next. Are we done with that? Thank you. Find the reaction forces. Okay. Bob pushes on a wall. So you might be thinking, okay, force of Bob on the wall. Therefore, the wall pushes back on Bob. Force of the wall on Bob. Bob's weight upon the floor. So Bob's weight is pushing down on the floor. Therefore, the floor must push up on Bob. Shorty kicks a football. It's fun to say that the football kicks Shorty, but it's really the football pushes back on Shorty's foot. And that's just a funny example because you're too old to trick or treat. Okay, next one. Usually I'd have a volunteer come up and I'd pick someone big and strong. And we'd hold two bathroom scales and we'd push against each other. And I'd say, okay, what do you read? What do you read? And they would read some number off the scale. And my scale would say the same number, but we wouldn't go anywhere. Let's say it was maybe, 30 or 40 newtons even. And we wouldn't go anywhere. Or 30 or 40 pounds because we're using scales. We wouldn't go anywhere. Then I risk life and limb for my class. I get on a skateboard and I get someone else to come help. But this time, I usually don't pick someone who's great big. I usually pick someone much smaller on purpose because I want to make a point. We get me on the skateboard, we push, and I say, read your scale. And usually it's very small force. It's, 0 to 5 pounds. It's very small. But I'm moving backwards during that. And the point I'm trying to make out of that is that it's not the forces at the hands that cause the motion. See, when me being Jim, when me and the student are standing on the ground and we push, we can exert a great amount of force upon each other. It's equal and opposite right here. We don't move. Okay. Very rarely have I ever had a student push hard enough to make me start sliding on the ground. But when we come here and I'm on wheels, now the resistance forces located at the student's feet, the pushing forces at the scales are greater than the resistance forces located at the wheels. And this allows me to start rolling backwards. Okay, and I do have many, many more examples, but I think that's enough for right now. And there's one more thing I want to talk about before we go forward, and that's terminal velocity. Because we're talking about equal and opposite forces, sometimes it's convenient time to talk about a net force here. Terminal velocity is when the gravity acting down on you is equal to the air resistance pushing back on you. So if these two forces are equal acting on you here, and this is not a Newton's third law pair, mind you, this is just a net force thing, because in reality, the action force is you pulling on the earth and the reaction is the earth pulling on you, that kind of deal. But when we talk about this terminal velocity idea, I'm a big fella, and most of you students are smaller than me. So what's the same and what's different? Our masses are definitely going to be different. Therefore, our weights are, hey, why can't I just have weight? I just want the weight. Our weights are definitely going to be different than one another. Our initial velocities, though, we both jumped out of the airplane. They're the same. Seriously, bell? How many times that bell need to ring? The acceleration of gravity acting on us is going to be the same. But because I'm larger, I will have a different amount of air resistance than you. Because I'm larger, it will take more air resistance to balance out my force of gravity. Therefore, I will accelerate for a longer time, and I will reach a greater final velocity during a skydive, which means my terminal velocity would be greater. And if the parachutes fail, I will strike the ground at a higher speed than you would. Good, hooray for you. But this is how terminal velocity works. It's where the force of gravity and air resistance balance each other out.